Okay. Um, Thank you for watching this video. I'm Jun'ya Kume, a postdoc at the University of Padua. And here I present a recent paper on the inflationary Chern-Simons interaction between pseudoscalar field and U-engaged field. And this is the outline of the talk. Let me start from the introductory part on the motivation to consider the specific type of model and interaction. Then I provide more detailed review of the phenomenology of the model, which is the production of gauge field and that of cosmological perturbations. Then I discuss our extension of this mechanism. Okay, so let's start. And as you know, inflation becomes a standard paradigm of early universe physics. And this is because it solves classical problems in Big Bang cosmology and at the same time provides the origin of temperature fluctuation of CMB. The simplest and elegant realization would be a slowly rolling scalar field, which we call inflaton, and the quantum fluctuation of inflaton generates the curvature perturbation of the universe, seeding the structure of our universe. While the CMB can be used to prove the profile of scalar perturbation, like this, we can also measure tensor perturbations. And precisely, we cannot directly see the tensor signal, but tensor to scalar ratio can be measured by polarization measurement. And again, in the vanilla scenario, tensor power spectrum can be simply expressed like this, and providing the bound on the inflationary energy scale. Indeed, this simple scenario is elegant, but I would say the real world will be more complicated. And the reason is the following. So for any models of inflation, there's one necessarily condition. That is, inflation must end and transition to the hot thermal plasma. And this generally requires the coupling of inflaton to the matter fields. And the question is, what kind of matter coupling we should consider? And for example, axion field, which has the approximate symmetry, is a highly motivated candidate for inflaton. In this case, matter coupling should respect this symmetry, and these actual currents of the fermions and Chern-Simons term of gauge field are often considered. And in fact, there have been active phenomenological investigations of Chern-Simons term since it predicts violent amplification of gauge field. And for simplicity, we do not consider particles charges under this gauge symmetry, but interested readers can refer to these studies, including one of my publications. But anyway, so if this amplification takes place during inflation, the profile of cosmological perturbations might be enriched. And as we will see later, this interaction is the polarization selective amplification of gauge mode. And interestingly, this leads to the generation of circularly polarized tensor perturbations. As there are numerous models of inflation, it is worth investigating such a characteristic tensor signal. However, this mechanism inevitably sources scalar perturbation as well, which turn out to be quite efficient. And moreover, the source perturbation is the product of gauge modes, so it's highly non-Gaussian. And the CMB constraints on non-Gaussianity put strong bounds on axion velocity. And to alleviate this issue, an alternative model has been proposed where the axion becomes spectator field and inflation is driven by some other field. And this makes the generation of curvature perturbations indirect via gravitational mixing of inflaton and axion perturbation. But to have a visible source tensor signal, axion needs to decay only a few e4s after the CMB mode crossing. So our question is there any other possibilities where we can have a characteristic tensor signals? Okay, so let's move on to the more detail on the source perturbations in this model. And first, let me illustrate the system we are working on. So on top of the inflation background, where homogeneous part of axion is slowly rolling, perturbations exist. And one is the ordinary vacuum fluctuation, and the others are gauge fields, and sourced by the axion velocity through this interaction term. And we assume negligible back reaction from the gauge field to axion background, and which is true for not so large sigma dot. Then this amplified gauge field in turn sources scalar and tensor perturbations. And this axion perturbation is sourced from two different contributions. One is inverse decay due to this operator, and the other is gravitational coupling. And in our paper, we consider two scenarios, and axion is inflaton or a spectator. And for the latter, the inflation is driven by a new scalar field phi. So we use this combined notation for scalar fields in our paper and following equations. All right. So the source components affect these observables: the scalar power spectrum, equilateral nonlinearity parameter computed from 3-point function, and tensor to scalar ratio. And as illustrated here, vacuum and source components are uncorrelated. So these observables can be decomposed like this. 0 indicates the vacuum and 1 indicates the source. Okay. And under our assumption where sigma dot is approximately constant, mode functions of source gauge field can be obtained analytically like this, and its characteristics are well understood. So here we just follow ordinary procedure of canonical quantization and to get the equation motion for gauge mode function. And it is controlled by this parameter xi. And here for only plus polarization mode in circular basis exhibits the tachyonic instability. And for convenience, we introduced this electromagnetic notation, and here we plot the dimensionless power spectrum of these quantities. And as you can see, this leads to the this growth from the due to this growth. You can see that at any moment of inflation, they are always peaked at the super horizon scale. And actually, this leads to the peak in the equilateral non-Gaussianity. And this is why here we consider equilateral non-linear parameter. Okay. And then these electromagnetic fields in turn source the scalar and tensor perturbations. This is the interaction term for the scalar fields in terms of canonically normalized variables. And as mentioned before, source terms for scalar can be classified in two types. The one is direct gravitational coupling, and the other is inverse decay. And in fact, there is a hierarchy between these sources. And in previous studies, computation has been done by including only this Q3 contribution. And source contributions can be evaluated with the green function method or equivalently in perturbation method. And for the single field case, it has been showed that scalar production is much more effective than the tensor one. as shown in this counterplot for the total scalar to tensor ratio, one finds the decrease of R when C is increased. In addition, C must be smaller than about 2.5 to satisfy FNO band from Planck. And for the two-field case, where phi is inflaton and axion is energetically subdominant, one finds this parametric dependence of sources scalar. So here, this delta n is the number of E-fold until axion decays after the CMB mode crossing. And this gravitational mixing yields epsilon delta n proportionality. And to suppress the scalar source, delta n cannot be too large, as I mentioned before. Okay, so these are what has been discussed for this model and mechanism. And now we propose an extension which drastically alters the observational consequence. So we consider the non-canonical kinetic terms for the scalar fields in our system. And such models have been discussed in the context of string theory, EV completion of the inflation model. But to the best of our knowledge, explicit construction of non-canonical axiom has not yet been done. But here we consider such an extension from the phenomenological point of view. And in fact, such non-trivial kinetic term is physically interesting. That is, both for the homogeneous part and perturbations, scalar mode acquires potentially large inertia. And this is also manifested in the sound speed of scalar mode defined like this. So large inertia corresponds to the smaller sound speed. And this new parameter causes parametrical changes in the observables. I mean, technically causes such parametrical changes, but intuitively, decreasing sound speed leads to the persistency and enhancing the nonlinearity of fluid. I mean, persistency of the perturbation and enhancement of the nonlinearity. So I think the enhancement of vacuum power and FNL can by small cs can be understood in this way. And what happens to the interaction with gauge field? So because of this parametric change in the relation between canonical variable and curvature perturbation, and in this change in this interaction term, the sourcing by the dominant inverse decay acquires 2 CS like this. And indeed, in the analytic solution for the single field case, you can see the CS square dependence here. And this means that from the standard case, source power spectrum and nonlinearity can be reduced by CS to the power of 4th and 6th, respectively. And notice that the modification is only in the scalar sector. The tensor would not be suppressed. So now we show main plots from our paper. So this left one is the standard case with CS equals to 1, and the right is CS equals to 0.1, and both for the single field case. And you can see the totally different behavior of the contours of R. And this is due to the suppressed scalar, and R can be increased, R can be enhanced by increasing C. And we found an observationally interesting window where the source tensor becomes a dominant component, and the R reaches to the value probable with future experiments, and at the same time, the FN band from Planck is satisfied. And but notice that vacuum non-Gaussianity is in turn increased, so we cannot go to arbitrarily small cs. So as presented in this plot, C can be up to 4.5 with current bound. And this is a factor of 2 difference from the standard case, but the sourcing exponentially depends on C. So in this way, the non-canonical kinetic terms completely change the observational consequence. And we finally show the two-field case where axion becomes a spectator. As I mentioned before, to have an interesting tensor signal, axion needs to decay with delta n about 5. So this delta n equals 10 is a bit large, and indeed, you cannot have a visible tensor signal, visible sourced tensor signal without violating FN band. However, this is also altered by the non-canonical kinetic terms, and here again we have an interesting observational window. And note that this window actually exists even for delta n equals to 60, meaning that now spectator does not need to decay. Okay, so let me conclude my presentation. So Chern-Simons interaction during inflation is widely investigated, and here we focus on U1 case. And it is known that polarization, it is known that source tensor becomes chiral, but it cannot be measured due to the efficient production of source scalar, non-Gaussian source scalar. But we found that inclusion of non-canonical kinetic term completely changes the result. And by small CS or large inertial scalar field, the scalar production can be well suppressed, and leading to the possibility of observing chiral tensor signal at CMB. And we note that explicit construction of such non-canonical axiom must be discussed, but the physics behind is general. I mean, it's a large inertial scalar perturbation. So this can be applied to any other scenarios with unwanted source scalar. And as a future work, we can consider computation taking into account back reaction from the gauge field to the inflaton background. And this is because the large C is now allowed, and the case with strong back reaction is worth investigating, I think. And I guess that large inertia from the non-canonical kinetic term plays a role there again, and non-trivially oscillatory behavior might be suppressed. Okay, so that's all from my presentation, and thank you again for watching this video.